My name is Arjun Verma, and this is going to be my Physics 2 third lab on bar magnets. So the purpose of this lab is to observe the magnetic force and fields in the real world through the use of bar magnets, such as the one below, and the magnetic field detectors in my phone. So you can see the bar magnet almost looks like a little bit of a dipole. It just has a magnetic field swirling around it from north to south. And our main concepts are going to be the PHYS law, which is a basic law used to find B field and to generate more complex impressions for finding force and field, like on the right, and the formula for the B field of a bar magnet, which is the KRN to the power of n over there. And then we're also going to be finding and analyzing B field. So the majority of this is based around magnetic field, like that's the main concept. And the details of our experiment is for this lab, we utilize the Magnometer app, downloaded on my phone to measure the magnetic field coming out of the bar magnet at multiple different points in relation to the phone as well as to the magnetic field of the Earth. So what we did is we mapped the distance from the bar magnet to the magnometer to the recorded field and linearized it with ln in order to gain insight. So you have to take the log in order to linearize this formula, kind of like how you saw earlier, it was exponential, so you take the log to linearize it. And on the left, you can see all my inputted data, and on the right, you can see the trend of it as, it shows ln of the B field versus lnr, and it is linear, right? So this is all my data on the left. As you can see, there's a clear correlation between the distance and the B field, and this is also the off-axis B field analysis. So you can see once it's off-axis from the Earth, the distances and the measures change. So they're different from the previous ones, and you can see how that changes experimentally. And you can make a couple observations and generalizations from this. Main thing being that the distance and relative position of the magnet / magnometer is important to the readings. The field increases as you approach the magnet in the x direction, and it becomes near zero as you move far away. As well as this, the position of the phone is crucial to ensuring the Earth's B field doesn't interfere with the readings, because if we're not in the correct axis with it, then it's going to interfere with our bar magnet's magnetic field. And because it has a big impact on it, it would make our readings kind of useless by adding a lot of noise to it. So yeah, after we've done all our experiments and we've calculated, the B field from different positions with respect to distance, we can utilize the distance dependence equation combined with the values we recorded and linearized, and the Biot-Savart law, we can calculate n and mu. And by using these equations on the right, through my calculations, I found that mu is equal to 2.45 a times m squared, and I also found that n was equal to about 3.12. K, mu, and n, all these things fitting into the equations on the right. So we also, I also did some GlowScript coding, and these are the results of the codes. After inputting the data from my experiment, I was able to find the B fields from different, inputs, like the B field perpendicular from different positions, as well as D and B at 45 degrees from a certain distance. And on the right, you can see all these arrows correspond to the B field at different positions. You can see how it changes when you're on axis, as well as when you're, off axis at an angle, and how that's very different from when you are on axis. And on the left is all my code, and the majority of this code being displaying the arrows, as well as calculating some of these magnitudes, right? And this was done in GlowScript Python, and I utilized all the GlowScript objects like the vectors and the arrows and whatnot in order to do this and, simplify it. So yeah, that was pretty much the brunt of my experiment and its observations and the analysis I ran with GlowScript, as well as, regular math. And there was a lot of potential errors that could have happened in my experiment. So one thing being that the magnometer may not have been precise, and the Earth's fields and other fields may have also had an impact because maybe it wasn't perfectly in the aligned way it should have been, right? I was placing it with my hand, so it might not have been perfect. As well as this, the bar magnet could be considered to not be a perfect dipole, even though it is super, super, super close. It might not be exactly what we wanted for the experiment. And these are our what-ifs. So the phone orientation with respect to Earth, if we changed the orientation such that it didn't compensate for the Earth's B field and laid our stick at some intermediate angle with respect to Earth's B field, then our results would have been a lot less accurate because the magnometer would have picked up the Earth's B field instead of bar magnets. And if we were to stick two identical magnets end to end and run the experiment again, you would most likely find the experiment would differ by the magnitude of the results approximately doubling, as the B field will be amplified as a factor of 2, since now there's just two bar magnets right next to each other amplifying themselves. And yeah, so that was basically my lab, all the experiments I did, the analysis I did, the conclusions I made from it. I had a lot of fun modeling B field in the real world and exploring a magnetic dipole and seeing how it interacted with the world around me. Yeah, thank you guys so much for listening. See ya.